Okay, so we talked about categorical data last hour. Now it's time to talk about numerical data. And numerical, quantitative, the other word for it. And what we're looking at here again are answers to that question that would produce numbers. And there are two types of numbers that it can produce. One of the types of numbers that it can produce are called discrete. The other type of number it can produce is called continuous. The simplest way I can describe discrete is a discrete numerical piece of data is something that can be counted. How many cars do you own? How many classes are you taking right now? How many children do you have? Those are things you would count. Continuous is something that would be measured. How tall are you? How much do you weigh? How much time did it take you to do this assignment? Those are all things that can be measured. Now, there are some gray areas in there, like time. Some people say, well, you can count seconds, but time isn't measured in just seconds. It's measured in minutes, seconds, tenths of a second, hundredths of a second. It can be broken down in between. No matter how close together two times are, you can always find a time that's in between them because you can break it down to a fraction of a second. That is continuous. That's actually one of the other definitions of continuous, by the way, is no matter how close together two numbers are, it's always possible to have a number in between them. Like for height, you have two people that are really close to the same height, but they can never be exactly the same height. They'll be really close. They'll be within whatever unit you're using to measure, but they might still not exactly the same height. There's always room for somebody to be in between them. Money is another one. Well, people might say, well, you could have a fraction of a penny, or when they're calculating interest, you can have a tenth of a penny. But when they put it in your account, they still round it to a penny. So money technically is counted. That is discrete. You count how many pennies you have. And there are other ones that are kind of gray areas. It's not necessarily a black or white situation. So let's look at discrete numerical data first. For dealing with discrete numerical data, we might organize it in a frequency table. We might ask, how many classes are you taking this semester, this term? Well, if you're not taking any classes, you wouldn't be a student this term. So 0 doesn't have to be one of the responses. Let's just go 1, 2, 3, 4, and 5. Being summer term, hopefully nobody's taking more than 5. Well, I mean, it is possible. There's a lot of one-credit classes like Microsoft Word, Microsoft Excel. Technically, to be full-time in the summer, you have to have 6 credits. Taking 6 one-credit classes is an extremely large load. I mean, a one-credit class is not 1/3 of the work of a 3-credit class. It's kind of deceiving that way. So let's say that in the students we surveyed, we had 23 were taking 1 class, 32 were taking 2 classes, 17 were taking 3, 8 were taking 4 classes, and only 5 were taking 5 classes. That's the frequency table. From that, we can make a bar graph. Or we could do a circle graph. Now the bar graph for numerical data is sometimes called a histogram. When we're dealing with numerical data, if we call it a histogram, there are two things that are different. First, always vertical. The bars always go up and down. The second difference might be easier to illustrate. Oh, let's do this. 5, 10, 15, 20, 25, 30, 35. So when I go to put my bars in here, it's going to look like this. One class is 23. Two classes is 32. Three classes is 17. 4 is 8. 5 is 5. What do you notice as I drew that histogram? What looks different compared to the bar graph? The bars are touching each other, and that is very intentional. Why would the bars touch each other in a histogram, but not in a bar graph? And it actually makes sense once you realize the reason. Well, first of all, would it matter in this bar graph if I put red first or blue first or green first? No, it would not. I could put those in any order, it would not matter. Up here, it makes sense to go 1, 2, 3, 4, 5, doesn't it? So there is a logical order for the numerical data. Up here, 2 comes after 1, 3 comes after 2, 4 comes. They kind of have a natural connection to each other. For categorical data, they do not have a natural connection. They're separated. There's no natural order, no natural connection from one to the next, no progression from one to the next. So putting the bars tight together is kind of a psychological thing of showing you that the data is connected. There is a flow from one to the next. There is actually a whole field of psychology, or a whole field of statistics on the psychological side of statistics. And that's one of the things, that's why they do the bars tight together in a histogram, is because when you're dealing with numbers, there's a logical flow from one number to the next. Then, of course, the circle graph would be the same. You would have to go in and you would have to determine the percent frequency from our table. Where'd my table go? There it is. We would have to come in here and we would have to add in percent or relative frequency. To do that, you'd have to find the total. What's the total here? 85. So you divide each of those by 85. 23 divided by 85 is 0.27. 32 divided by 85, 0.38. So you'd make your circle graph. 0.27 is slightly more than a quarter. So that's one class. 0.38. Well, that's like the 37 and a half. That's 1/4 plus another eighth. That's about like that. That's two classes. Three classes, the 17 divided by 85. Didn't work. 0.2 That's a little bit less than a quarter, so it's not like there. That's going to be 3 classes. And then that's going to be 4 and 5 classes. So it's exactly like doing our categorical data. Any questions? Where it becomes a little trickier is when we start dealing with continuous numerical data. Continuous numerical data, because it's measured and because there's so many possible values for the result, cannot be listed individually. For example, if we're looking at height and frequency. Well, if I'm listing the heights of people, I might have 63.2 inches, 73.1 inches, 67.4, 70.3, 71.9, 68.7, 70.1, 65.2. I mean, it's possible to measure several people's heights. I mean, I could measure 30 or 40 people's heights and never get 2 that are exactly the same, or 2 that measure the same. Remember, we said they're never really exactly the same. There's always slight variation. But if we're only measuring to the 10th of an inch, it's possible to get 2 people that are to the same 10th of an inch. But I could measure, like I said, 20 or 30 people and never get 2 that are exactly the same 10th of an inch. So I'm not going to list all those out for my height here. So what I'm going to do is I'm going to make ranges. Let's say that my smallest person in this list ends up being 60.8 inches. And the largest ends up being 76.2 inches. So basically I'm going from 60 to 77. So what I'm going to do, and at this point there are some more exact ways you could do this, but for this class we're not going to get into that. If this were a statistics class, we would talk about how to develop, how to get those ranges and whatever filled out. I'm just going to divide this into 3 ranges. I am going to go from 60 to 65.9, 66, 71.9, and 72 to 77.9. Notice that goes below the smallest number and above the largest number. This might be considered a little sloppy because I'm a little bit further away from the smallest number on bottom, or a little bit further away from the largest number on top, I should say, than I am the smallest number on bottom. But it's not bad. So then I would go through and I would do the same thing. I would tally. Okay, 63.2 is here, 73.1 is up here, 67.4 is in here, 70.3 is in here, 71.9. And I would tally them up. Well, we're going to pretend we've already done that. And we're just going to get frequencies of 27, 46, and 27. So now we're going to organize that frequency table in a histogram. And it's going to look pretty much just like the histogram we made for the discrete data. Only instead of having a single number down on the bottom, we have these ranges. Up the sides here, we have to go to 46. So I'm going to go 10, 20, 30, 40, 50. And once again, the bars will be tight together. So 27 is going to look like that. 46. I'm overshooting here. There. And again, the bars are tight together because there is a natural order to the categories down here, and there is a flow from one to the next. If this were a statistics class, we'd actually take the next step. We'd talk about the shape of a distribution. In the shape of the distribution, what you do is you connect the center of the top of each bar and you draw a curve through it. Now, with only 3 bars, it's not much of a curve. But that curve then tells you the shape of the data distribution and stuff like that. There's another type of graph I want to show you. And this deals with a totally different type of data. What we were looking at before, we had that random variable, that question that was being asked. And we had categorical responses, numerical responses. What we're looking at here is a numerical variable, but we're not asking several different people or looking at several different items, I guess, and looking at the numerical response. We're looking at only one item, but we're tracking it at different periods in time. It's called time series data. Whereas all the other data was a snapshot. In fact, one of the things we'll discuss on Thursday is it's extremely important to get all that data collected at a single time. That if we're going to do that type of data, we've got to get it all collected in a very small window. In fact, we might talk about it a little bit yet today. Time series data is intentionally gathered over a period of time. For example, you might look at WITC tuition. Cost per credit. Let's go 2000, 2005, 2010, and 2015. This is the year. This is the cost per credit. So in 2000, it was 98 bucks a credit. 2005, about 114. In 2010, it shot up to 149. And in 2015, it actually dropped slightly to 144. Our graph that we use to graph time series data is called a line graph. And in a line graph, time always goes on the bottom. Now, in this case, our time that's being expressed is the school year. So we label that as year. And of course, we're going to label those years 2000, 2005, 2010, 2015. And now I'm going to avoid doing that broken axis here, although this would be a spot where it wouldn't be a terrible idea. 50, 60, 70, 80, 90, 100. Might have to extend it a bit. 10, 20, 30, 40, 150. So in 2000, it was 98 bucks right there. 2005, 114. 2010, 149. 2015, 144. So it looks like that. Now, a lot of people are tempted to do this, connect that line down through there. Don't do it. That line is meaningless. It's actually distracting and deceiving because there was no point down here where tuition was $0. But what you can get off of this is, one, you can tell very quickly where it was increasing because the line has a positive slope. Tuition was increasing from 2000 to 2005 and from 2005 to 2010. It was decreasing from 2010 to 2015. You can also tell where it was increasing or decreasing the fastest. The line is steepest right here, so that's where it was increasing the fastest. The steeper the line, the faster it was changing. So a line graph is very good at determining where it was increasing or decreasing and which one was going the fastest. Our other graphs have their strengths as well. I mean, a pie chart is best for showing a number as a portion of a whole. Like you might, a great example of a pie chart or a circle graph being used would be your household budget. This is how much money you bring in every month. This is where it goes. So you can see how big of a slice of your income goes to each item in your budget. That's a great way of explaining it. Your bank does that for you? That's cool. Oh, if you're using your debit card, it tracks what you're spending it on. Okay. Sure. That's cool. A bar graph or a histogram, either one, is best for telling largest and smallest. I mean, I can look at this graph up here very quickly and say green is the most popular, blue is the least popular, blue is the shortest bar. I can also very quickly compare. Hey, which color did people like better, blue or red? Well, I can look up here and see red is taller, so red was the one that was more popular than blue. So the bar graph is good for that comparison. What any of our graphs are poor at. If I go back down into our line graph. If I look at this graph, can you tell me exactly what tuition was in 2005? No, you can't. You can tell me it's slightly more than $110. You might be able to say it's like maybe 112, 113, 114. But you can't tell me exactly what it is. Graphs are no good, are very weak at doing exact numbers. Graphs are for quick comparisons, not exact numbers. If you want exact numbers, you go back to a table like this. The table can give you the exact numbers. Why do we bother with the graph then? Well, look at that table and tell me when was the price increasing and decreasing. You can do it, it just takes a little bit longer. In the graph, you can look at it and visually pick them out very quickly. So there's a place for each of them. Now, another type of display, as we work on, we're transitioning into more statistical analysis here over the next couple of classes, is called a dot plot. And what a dot plot is just a number line with results put on it. Let's say I want to look at test scores from the last test. Let's say the lowest score we had was a 60. And let's say nobody scored above a 90 because that's where I ran out of space on my page. On this number line, pretend that's straight and not sloped, I am going to plot with a dot the result of each test. Now, in this class, there's only 10 people, so I'm going to pretend I have a few hundred people in the class to make this work well. So the first test I grade might be a 72, so I put a dot above the 72. I might grade one that's an 84, so I'm going to put a dot there. I might grade one that's a 76, a 77, an 86, a 74, a 67, another 76, an 81. And as I grade the tests, I put dots on here to represent their results. And as I'm putting those dots on here, you notice that some spots keep getting repeated over and over again. Other spots don't have any values there. But if I grade enough tests and keep putting enough of them on this number line, what eventually happens is the dots build up and they form a definite shape. If I trace kind of the top of the dots, and there might be some over the top that don't quite fit in, whatever, I get the shape of the data distribution. Tomorrow, as we start talking about analyzing data, we're going to look at describing the shape of this distribution. Well, the curve I have here looks like a bell. You've heard of the bell curve? Well, that's where it comes from, is you plot the data there and it forms the shape of a bell. Mostly in the middle, and as you move out, it gets lower and lower. The technical phrase for that is called the normal distribution. Because in nature, that's the shape that data normally takes. If you look at lifespan of animals, it looks like that. If you look at size of animals, all sorts of different things, if you look at them, they look similar to that. If you look at the high temperature on this day throughout history, the temperatures will be distributed in a shape similar to that. Okay, so let's take a step back and talk briefly about gathering data. We talked about that random variable. That random variable being the answer to a question. It is sometimes not that easy to define what the random variable is or what our question really is. Like if we've got an election coming up and we want to try to do a study on trying to predict who is going to win the election, the question we're asking is not really who's going to win the election, because there's no way we can do anything to gather information about that. The question we're really asking there is, who are you going to vote for? Well, in that question, the word you needs to be defined. That's the population. The population is the group to be learned about or studied in the question. A lot of people think when we're asking, well, who's going to win the election, that the population are the candidates in the election. That's not true. Their behavior really doesn't answer our question. The behavior that answers the question is the voters. Who is going to vote in that next election? They're the ones that are going to determine the answer to that question, not the candidates. It can sometimes be very tough to define the population because, like I said, that who's going to win that election, well, you might define the population as all registered voters in the area that the election is going to take place. Well, that's not your population either, because there are registered voters out there that haven't voted in years. If they don't plan to vote in this election, we don't care what they think. What our population really is all the people who are going to vote in this election. Well, there's an issue with that because some of them might not even know yet whether they're going to vote. So to study a population, we use a sample. And what a sample is simply a smaller group selected from a population. There are several reasons to select samples instead of populations. One of them is just what I said. Difficulty defining the exact population. If they don't know whether they're going to vote yet or not, how do we determine whether they're in the population yet or not? Number two, time. If we're in a large city or maybe even a whole county, we might not have time to try to contact every voter and ask them how they're going to vote. So we take a smaller sample. Then, of course, the one that rules the world, money. Every person we contact costs us something, whether it's paying somebody to do it or other bills. There aren't long distance phone bills for the most part anymore, but there is a cost involved in doing it. This other one, the time that I was saying up here is the time it takes, your time. You only have so much time to put in gathering this information. You don't have time to contact everyone. The next one I'm going to talk about deals with time as well, but it's changes in the population over time. In an ideal world, you would determine your question, determine your population. You would select your sample then from that population. And then what you would do is you would gather the information from that sample in an instant. You just snap your fingers and you have all the information from everybody in that sample right now. Well, that obviously isn't practical. It might be okay to gather some of the information today and then some of the information from the rest of the sample tomorrow. But if it gets spread out over 3 or 4 or 5 weeks, that is not good, depending on the situation. Like in a political campaign, let's say that I am going to survey 200 voters. I talked to 100 of them today, and I'm going to talk to the other 100 tomorrow. But tonight, candidate A goes on television and says something really stupid. Maybe he admits to getting drunk and rolling his car accident or taking stupid pictures or whatever. He says something that turns people against them. Well, some of those 100 people that you interviewed earlier today might have changed their mind. Well, definitely the people you interview tomorrow are being interviewed under different conditions. And that's really the big thing here, is changing conditions. There is something that's now known about that candidate that was not known by the previous set of people in the sample. Now, the fifth one is not necessarily for political surveys or things like that. It's more for industrial testing and quality control. And I'm just going to call it destructive testing. In quality control in industry and manufacturing, sometimes you produce parts that have to have a minimum strength requirement. So you take those parts and you put them in a machine. Let's say you've got a machine that's going to pull them apart, pull on them. So you put your part in there, and this machine pulls on it until they break. Well, you might say, well, why don't we just pull on them at the force that they're required to hold? Well, that's a good idea, but by applying that force to it, you can actually damage the part, and you don't want to necessarily ship it out after you've tested it anyway. The other thing is, in order to ensure that it holds that much force, you want to make sure it can actually hold a little bit more for a safety margin. So you're going to stretch it until it breaks and measure how much force it took to break. And hopefully that force it took to break is more than the force that's required for what it's supposed to be. And as long as that's happening, you go on your happy way. Well, the problem is, once you test a part, it's broken. Can you ship it to a customer now? No. What would happen if you tested every part? Yeah, they'd all be broken. There'd be nothing left to sell. So that's why you have to take a sample there. Is you got to figure out, well, how many can I test and be sure that my parts are good, but not destroy all my ones that I can sell. I still have enough to sell to make a profit. So that's why we take a sample. Information gathered about that sample is called a statistic. And it's an information that describes the sample. And most of the time, it is just the information that was gathered in your survey or your test or your experiment or whatever you did. It's the information that was gathered from the sample. But technically, a statistic is just any information that describes the sample. Now, the biggest thing is, as related to the random variable. There's a difference between describing the sample and defining the sample. Defining the sample would be saying, okay, we surveyed 200 people. They all lived in this region. They were between these ages. That's describing the sample or defining the sample. It's not, has nothing to do with the random variable, who they're going to vote for. The statistic has to describe who the result of that random variable, in this case, who they're going to vote for. There's something called a parameter that describes the population. And again, it has to be related to the random variable. You can't say, well, the whole population is, there's this many registered voters in this region, and whatever. That's defining the population, but it's not describing the population in terms of the random variable. A parameter is very seldom known exactly. Usually we use what we got in our sample to take a guess at the parameter. Let's say we survey 200 people and about 120 of them say they're going to vote for Canada today. That's 60%. So we might turn around and say we have reason to believe that about 60% of voters will vote for candidate A. That is a parameter because we're describing all voters there. That's describing the population. Even though it's not necessarily exact and we use the information from the sample to determine it, we are using that statement to describe the population. So we've looked at why we take a sample. The next big question is how. And when it comes to sampling, there's something called a representative sample. And a representative sample is the goal of any sample you take. And what it is the sample statistics are equal to or really, really close to the population parameters. If we're back to our voting survey again, if we take a sample and we survey that sample and 60% of that sample say they're going to vote for candidate A, but only 45% of the whole population actually votes for candidate A, then that's not a very representative sample. If about 60% of the sample say they're going to vote for that candidate, then for it to be a good sample, that means 60% of the population better be planning on voting for that candidate. It doesn't mean they necessarily end up voting for that candidate because something might change between now and then. But at this moment in time, 60% plan to vote for that candidate. So how do we get a representative sample? There are two factors, size and selection. Sample size is very tricky. Generally, bigger equals better to a point. If the size of the sample gets to be more than a certain percentage of the population, well, it's kind of fruitless to take a sample. Why would you not just do the whole population? Again, that's a statistics question, not a pre-algebra question. So we're not going to get into that. Well, how big is too big and how big does it have to be before it's valid? And too small of a sample is bad. A lot of times they'll say 30 seems to be the magic number that a lot of textbooks use. There's reason behind that because a sample size of 30 is the minimum to determine whether it's really a normally shaped curve or not, and to make that assumption. Otherwise, you have to know that about the data before you start. But really, there's a lot of complicated things that can go into sample size. So we're not going to discuss a whole lot about sample size. Selection is really the more important one anyway. Sample size, make it bigger, makes it closer to the real, more likely it is to be close to the real parameter. Selection, however, is just absolutely vital. So let's talk about selection. Let's say you decide you want to survey people to see how the election is going to go. So you go out and stand on the sidewalk in front of your house and interview people walking by. Ask them who they're going to vote for. Is that a good sample? Okay, that's a good point. That's what's called a convenience sample. If there's a lot of people walking by your house, you might get 200 or 300 responses. But is it still a good sample? Well, a convenience sample, you're taking easy results. You're just going out there and taking what's readily available to you. And at this point in a math course, you should understand that easy is usually not better. For a sample to be good, it must be random. Random means every item in the population has equal chance to be in the sample. Well, if you're standing out in front of your house interviewing or questioning people, does somebody that lives on the other side of the county have much chance of being in that sample? No, not unless they happen to be walking by your house right now. So no, that's not it. If you get phone numbers out of the phone book and you randomly select people and you call them all at 2 o'clock in the afternoon, is that a good sample? No, because people that are working or can't answer their phone at that time can't be a part of it. So you have to be very thoughtful in making sure it's random. You can go through a phone book and randomly pick names and phone numbers, but the way you call them, you've got to call them at different times of day too to get people that work, so you get those people that work during the day or may work night shift or whatever, so they all have an equal chance of being called upon to answer that question. There's something even stronger than random, which is called simple random. Simple random has to do with the sample size, the whole sample. The number of people that you choose to put in a sample is called N. So if I chose to survey 200 people, my sample size N would equal 200. A simple random sample, if N equals sample size, is that all possible samples of size N have equal chance. A simple random sample is kind of tough to draw. It sounds relatively easy at first. One way, like if I wanted to survey students to see how much they spent on textbooks, I could take all of the students at WITC. I should define my question better. If I want to know how much students at WITC spend on textbooks last semester, I've got to define that population very narrowly to make sure I can do it. I would take the names of all the students at WITC last semester, throw them in a hat, and draw out however many I want for my sample. Let's say I determine I'm going to survey 30 people. I'll draw out 30 names, and I'll survey them to figure out how much they spent on textbooks. That is a simple random sample. But in real life, that simple random sample doesn't always work. A form of random sample is a cluster sample. If I am going to go door to door and ask this survey, let's say here's my city. This is going to be a small city. Would it make sense to randomly select people? So I've got one here, 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 one there. So that going door to door, I have to drive all over the city to get to each of those houses. That would not make much sense, would it? I'd have to do a lot of traveling around. And if somebody wasn't there, I'd have to go a few blocks away and come back and whatever. What makes more sense is a cluster sample. You divide the population into groups. Then you select whole groups. So for example here, the city is divided into blocks. I might randomly select blocks. I might select this block, this block, this block, this block, and that block to survey. That way I can drive, I can park on the corner and just walk around the block knocking on doors. If somebody isn't there the first time around, by the time I get all the way around the block, I can go back and check them again. And then I can go to the next block and park. I'm not running all over the place. So there are a lot of times where cluster samples are very, very useful. But it's random because everybody in the city has the same chance of being selected, because every block has the same chance of being selected. It is not simple random because a sample that has one person from each block isn't possible. There's also called a systematic sample. A systematic sample is what's often used in manufacturing for quality control. You randomly select a starting point. Then the system does the rest. So let's say that in a manufacturing setting, you need to test every 100th part that comes off the line. Well, to make it random, what you're going to do is at the beginning of your shift, you're going to select a number 1 to 100. And let's say that number might be 47. So you select 47, you're going to test the 47th part, the 147th part, the 247th part, 347th part, and so on. Notice it's random because every part has equal chance of being selected. But it's not simple random because it's not possible to test two parts in a row. There's also something called a stratified sample. What a stratified sample is, similar to a cluster sample, you divide the population into groups. But now instead of selecting whole groups, you select from each group. This happens in companies a lot if they want to do like employee satisfaction. They divide the employees into managers, salespeople, production, secretarial or office staff. Then they'll randomly select, so many from each. Like let's say there's only, 10 managers in the building, they might select 1 or 2 managers. If there's 300 people working production, they might select 30 people from production and so on. So that way they know every group gets represented and they get represented in the proportion that they are of the whole amount. So those are just some examples of sampling. Again, a stratified sample is random, but it's not simply random. And in statistics, if we talk about statistical analysis, simple random is really where it's at. For most of our statistical analyses to work, the sample really needs to be simple random. But you can see in practice, most of the time it is not simple random. Now you might be sitting here thinking, well, what about this is going to be in the homework? Well, the homework does not talk about taking samples and sample strategies and all that stuff. The homework just talks about organizing the data and things like that. This discussion goes into what we're going to talk about on Thursday, which is now analyzing this data. But really, to me, it's important that before you start analyzing data, you know how to get it, where it comes from. Because if you do not gather the data well, once you do with it, once you've gathered it, is meaningless. I can analyze the heck out of a bad set of data. It's still a bad set of data and it really tells me nothing. So there is a new quiz that is due tonight. At 11:59 p.m. And there's a new homework. This is due for Thursday. I was going to offer an extra credit question, but we only have about 20 minutes left today, so I'd rather have you use that time to get started on homework or finish up homework from yesterday. We'll throw the extra credit question out there on Thursday. The next test is next week, Thursday. It'll be on the last day of class. We'll lecture on Thursday. There is a very, very slim chance we'll get to it Tuesday, but I think we need more time to review, I think. I'm planning all day Tuesday as being a review for the test.